Is this thing on? Okay, it's on. So this is going to be quick. It's just a little bit of housekeeping. Just some stuff that I noticed. So I realized that actually the cursor is supposed to be allowed to move when you're in single mode so that you can, step stuff and look around. And I realized, well, that also makes sense in the undo mode. So I just want to quickly do that. Easier said than done, I suppose. So yeah, actually we don't want this. And instead of this, we want that. Okay, so let's just put some random stuff in here. Then go into undo mode so we can move the cursor. We can look around all the while undoing stuff. Good. And and redoing. Okay. So that takes care of that. Then there was something else I noticed in the post condition function. It doesn't actually check the registers. There's a couple of places here where it checks if type is equal to gate, but actually I wanted to check for is component. It might only be in here. Yeah, so see right here, this should actually be is comp for is component. There is another thing I wanted to do, which just makes things a little bit easier. In the interact mode, where is the interact mode being handled? Else if o.type is equal to, geez, what did I call it? Register? Line 567. How many lines do I have in this tab? I should start splitting this up a little bit. Forget what I needed to look at. Oh yeah, that's right. Oh, down here in place component. Yeah, it is reg. How do I get the delay length? No to len. Okay. What's R? T off. Well, this is a little cheesy, but local max, or no, I don't know, n is equal to, do we have left shifts in here? Yeah, nice. One left shifted by T no to len of O dot T t off plus 16. And then here, I'm just going to put so sue me. I mean, it's ugly, but, you know. Now we will do O dot state equals O dot state. Oh, wait a sec. Wait a sec. So this len is 1. Yeah, so this should be -1. Right? No, that's right. Actually, we can leave this here. O state +1 mod m. Let's see if that works. The reasoning being that it would be nice if we could like change the state of registers. Ooh. Oh, is tnode to len? It's a local table. Okay. All right. Well, in that case, if it's just a local table. I'm listening to some old chiptune stuff. Ah, shoot. Attempts to perform arithmetic on field. Strange. Oh, well, first of all, that should be like that. Ah. I think the calculation is wrong. Log m equals n equals 2. Now, I see the problem. Actually, I think this is correct. Yeah. Okay, good. All right, now let's try these guys. Okay, great. Yeah, so the reason for that, well, you know, in general, it's useful for the user to be able to interact with things. So there's no reason not to. But also, there was a intended use case of this, which is like, it just makes it a little easier to feed stuff in. You know what I mean? So now what I want to do is do one of these, and now I need one of these. I'm trying to make a little pulse generator here. So what I'm going to do is I'm going to make an AND. Actually, I want to put it here. make an AND gate like that. And now I think I need a NOR gate like this. So now I think this should generate pulses whenever I change this. It only works on the rising edge. This is a little too fast. Oh, shoot. Shoot, I can't interact. Okay, I'll just turn the speed way up. Yeah, I think this should actually be one of these, maybe. I'm really struggling with this. All I'm trying to do here is make a pulse. Like every time I change this, I want it to make a pulse. Oh, no, actually I do. Want this. Okay, hold on. So just like this, we can detect, shoot. Man. Okay, hold on. So just like this, it should detect. Yeah, it does. It detects the edge from 0 to 1. Now I also want to detect the edge from 1 to 0. Whoops. So what I need is this, I think. Okay. This is the same gate. Wait, is this just that? Oh yeah, it is just that. So now, okay, great. This should do it. Okay, great. So now every time we hit this, we get a pulse. Now, the whole reason for me to do this was because, say I had like I wanted to input a multi-bit value, like say an 8-bit value, over the course of 8 cycles. 1, 2, 3, 4, 5, 6, 7, 8. And let's wire this around for convenience. So now every time I hit this guy over here, this does a circuit loop. So let's say I had the value, you know, this value here. So now the output is 1. Whoops. So now if I do this, it shifts by 1. So 1, 0, 0, 1, 0, 1, 1, 0. Yeah. Now, why did I do that? Because when you're doing stuff in Redstone and Minecraft, it can be quite a pain and just annoying. Okay, those mean the same thing. It can be cumbersome, laborious, an encumbrance to have to do like 8 parallel full adders. However, if you're really clever, you can shift an 8-bit signal into just one full adder that you build once. Yeah. So I kind of want to do that. Let's put another shift register down here. By the way, shift registers in Minecraft are so jank because depending, I'm not kidding, depending on whether your circuit faces north or south in game, it'll change the timing. Not to mention that shift register, like what are these called in Minecraft? The repeaters. The repeaters, they behave differently for 1s and 0s. It's just a ridiculous mess. Now, suppose, okay, before we do crazy things like doing an adder, let's just do a simple OR, all right? Let's say I wanted to take the value in this shift register and OR it with the value in this one. So this or that will be 0, 1, 1, 1, 1, 0, 1, 1. Okay. So let's put an OR gate right here. Now here's the trick. Let's put our output shift register here. Whoops. We can do an adder in a second. It won't be that hard, but I need to think about it because we need to worry about the carry. 1, 2, 3, 4, 5, 6, 7, 8. Wire that up like that. And now here is the trick. Because this calculation takes 1 cycle, we will latch this 1 cycle later. Divot a bit, divot a bit. I need one of these. And just to make things easier to see, let me clear all these out. So if I hit this guy 8 times, the OR of these two signals being computed by this OR gate right here. Let's make it the AND. Let's just make it the AND. It'll be easier to see what's going on. So this and that is mostly 0, so we have a 1 in bit 3, and we have a 1 in bit 7. Oh no, bit 6. So let's hit this once to see what happens. So what will happen is these will do a circular shift, and this and that will be written into here. And I'm just going to hit it 8 times. I don't want to wait. 1, 2, 3, 4, 5, 6, 7, 8. Ta-da! There we go. So with just like a 1-bit calculation. Like I didn't have to have 8 parallel AND gates, which would not only be a pain because I would have to draw them all, but it's also a pain because you have to wire them, and the wires can get really ugly. Yeah. So let's see if we can do an adder, which would be interesting. Now, right now I'm just like playing with it now, so you know. Let's think about the adder. So first of all, okay, let's draw the carry, which is going to come out of our adder circuit. We'll give ourselves this much space for it. So the carry is going to come out over here, shall we say. Now, how do you make a full adder? Oh, geez. I really need to think about this. Now I'm just procrastinating by arbitrarily tidying up the wires. Anyway, the sum is the XOR of all three. The carry is whether at least 2 of them are high. Right. So how do I do the XOR of all 3? I guess I could just do 2 pairwise XORs. I mean, you know, it's fine. So that's the first XOR. And using our fancy interact here, we can test it out. 1 XOR 1 is 0. Yep, okay, that's working. And now we need to XOR in. Actually, it'll be a little bit more convenient to do this down here. Well, right, I don't need the AND might be useful separately, so I'll keep that. Because I was able to simplify the other one a lot by doing that. Whoops. Now we can try it out. 0, 1. Yeah, okay, that's working. So now our output carry, I will really have to think about. So we have the and right here. This is going to seem a little unnecessary, but trust me for now. Let's get the and of these two. And I also want the and of these two. And I want to OR these three together. These three ands together. Wait, what's going on here? Oh yeah, okay. Yeah, this is what I meant to do. So I kind of want to test this out here. So ignore this right now. This is an unfinished sum, but this should be the carry. So if at least two of these inputs are 1, the carry should go high. So not high, good. Not high, good. High, good. Not high, good. High, good. High, good. High, good. Not high, good. Okay, I think that's working. So this bottom signal here, which is the carry, is the OR. In fact, let me make it a little bit more explicit. This is equivalent. Well, oh, interesting. Actually, this adds a cycle of delay, which is fascinating. But this makes it a little more clear what's going on. So this is an AND gate of the top input and the middle input. This is an AND gate of the top input and the middle input. Oh shoot, that's not. Wait, what? This is an AND of the middle input and the. Yeah, wait. Hold on. These two signals are the same. How come this is working? Yeah, it's not working. Was it working before and I broke it? Well, anyway. Let's just fix it. I thought it was working. So correct, 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 not correct. Oh. It's the wrong gate. No, wait a minute. No. What's going on here? Actually, I think I need this. Let's try this. So that's right. That's right. That's right. That's right. That's right. That's right. And that's right. Okay. So the carry output is working. So now we need to fix the sum output. So right now this is the XOR. Okay, yeah, so now we just need to XOR that with the input carry. Wait a second. If I want to XOR this, let's just draw it in, then we can optimize it later. No. Okay, so now this should be a full adder. So let's try out all the possibilities. 1 plus 0 is 1. The top one is the sum, the bottom one is the carry. Okay. 0 plus 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 1 is 2. And 1 plus 1 is 3. Good. So this makes a full adder. And now here's the trick. Okay, let's put our output shift register here. 2, 3, 4, 5, 6, 7, 8. Like that. Now we need to know so you'll see. Because we need to loop the carry. Actually, I can just do it here. We need to loop the carry back into the circuit. So now the big question is, when do we release the latch on these guys? And it's all just a question of getting the pulse at the right delay. Excuse me. So what is the compute time for this guy right here? It is 2, 3, 4, I think. Is that right? Yeah, I think it's 4. So we need a delay of 4 on this. Well, hold on, I'll put it a little bit closer to. Oh no. So we need a delay of 4. And when is the carry valid? 1, 2. It's just 2. So now, yeah, this should work. I mean, unless I counted stuff wrong. So let's, we'll do this one step at a time. So let me clear out this guy right here. Okay, now we have the value 6, 9, nice, plus 5a. So let's ask good old Google, what is 0x69 plus 0x5a? It's 0xc3. That is what we expect to see at the output. But we'll follow it step by step here. So right now at the output we have 1 plus 0. And we've reset this carry register to 0. So when I hit this pulse guy up here, we should get 1 in this first output register and a 0 in the carry register. So let's do that. And is that what we got? Yes. Now we have 1 plus 0 plus 0. So we should get another 1, and the carry should still be 0. Okay, good. Now we have 0 plus 0, so we should just have zeros all around. And we do, good. Now we have 1 plus 1, so this next one should be 0, but the carry should go to 1. And that is what happens. So now we have 0 plus 1 plus 1, which means that this should also be 0, but the carry will stay at 1. Which is exactly what happened. Uh-oh. We have 3 zeros here? That's not right. Or is it? Maybe it is right. Well, we'll see. This is the LSB right here, so we still have 3 more ticks to go. Oh yeah, C3. Actually, I think that is right. So anyway. So we have 1 plus 0 plus 1. So same thing. We'll shift another 0 in here. The carry register will stay at 1. Yep. Now we have 1 plus 1 plus 1. So we should shift the 1 in, and the carry register will stay at 1. Yeah, great. And then finally, 1 plus 0 plus 0 is 1. So the carry register goes to 0, and we shift in a 1. So here's our original input, 0x69, then 0xa5, and their sum is 0xc3. Not bad, eh? Let's do it again just for fun. 1, 2, 3, 4, 5, 6, 7, 8. C3 again. Now we do need to be careful because we do need to clear this last output carry on the 8th one in case it's still high, like if we got an overflow. But whatever. Let's add some different numbers together. Let's do, I don't know. This is 42, so this should I'm trying to think of an interesting test case. You know what? Let's roll a random number. Random.org. So let's pick one number between 1 and 256. Oh no, 0 and 255. 228. So 228 in hex is E4. So bam, 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 and bam. Roll another random number. 250. Man, how come I'm getting big numbers here? So that is 250 in hex is FA. Bam, 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 and bam. So now 250 plus 228 is DE, with an output carry of 1. So let's shift this through. 1, 2, 3, 4, 5, 6, 7, 8. 1101, that's D. 1110, that's E, and we have an output carry of 1. Now this isn't automatic. I have to like manually hit this 8 times, and then if there happens to be an overflow, I need to manually clear it. But you could automate this, I suppose. Actually, I'm not really sure the best way to automate that. Anyway, it does work. So this is an 8-bit. We could easily add more bits by just extending this shift register. So this is a 1-bit full adder, properly rigged such that you can add two arbitrarily long numbers and save the result. Yep, that's that. Okay, what next? I'm starting to get a little coded out here for today. Yeah, I think this is a good time to stop. I guess I can push this to GitLab. Minor improvements. Well, no, I should be a little more descriptive than that. Allow movement, special modes, interact with reg state. Got touch.